everyone and welcome to the channel. Today we are going to look at the paper called Autobidding with Constraints from Google 2019 by Aggarwal, Badanidiyuru and Mehta. This paper is important because it provides a very important and famous result that the uniform strategy, uniform bidding, is an optimal strategy when the auction is truthful. And this is sometimes the main argument why systems such as Google AdWords, Meta ads, and other systems should implement the so-called VCG auction, because that one is the truthful auction. So we're going to take a look at the argument, and the paper has more content, but our goal today is to understand the proof of this result. First, let's understand the setting of the paper. So we have the advertising system in the middle here, and the advertising system is running the auction. The auction is here. This is a real-time auction. So here we have users. They are, watching the stuff on their phones, or maybe they're searching for something. And in the background, the phone is sending requests for the ads to serve to this user. And the choice of the ads is like a multi-stage process, which includes retrieving of ads that might be relevant for this user, and then running a real-time auction on it. And in the current modern systems, the advertiser is here. The advertiser is here, and this advertiser has some competitors. In modern ad systems, the advertisers are not bidding directly in the auction, because auction, it's just impossible to put the manual bids on all possible contexts. The whole system is data-driven system, and in the data-driven system, the automated bidding is adopted. So now we have this intermediary between the advertiser and the auction, and here we have this intermediary, and we are going to call this intermediary the bidder. And the bidder is acting on behalf of the advertiser. So even though it belongs to the ad system, the assumption here is that the bidder is a robot that acts in the interest of the advertiser. But the bidder has access to real-time information, including the context of the auction and the estimates of the click-through rate, the CTR here. The ad system is running machine learning, real-time inference to figure out the click-through rate of this user for this particular ad in this particular context, as well as the conversion rate and maybe even like an estimate of the expected order value, which is the amount of money that the user is going to spend on the purchase. And it's just completely impossible for the advertiser to provide the bids for all possible contexts and for all possible users in all possible regions and demographics and so on. So instead, the bidder, this robot here in the middle, is the one who is going to provide the bids, and the advertiser is going to set the goal for the bidder. So it's basically saying, I want to spend this amount of dollars, and providing a constraint on the performance of the ad. Typically, the constraint is expressed as a return on spend, so-called ROAS. And this ROAS is just that how much value did advertiser get from advertising in the form of purchases from the users, compared or divided by the amount of money advertisers spend on the advertisement. So in this paper, the main question is how this bidder should be actually, what is the strategy of the bidder? What is the optimal strategy of the bidder? And this has a connection to the properties of this auction. That is the main subject to characterize the optimal bidder strategies, and with respect to the formats of the auction. And there are some simplifications in this paper. The simplification is that the competitors, they are considered like they are not strategic. So they are fixed, they are frozen. And our advertiser and our bidder are able to devise the best response strategy. So this means that they kind of get the information, maybe indirectly, about the competitors, and they can choose how they want to bid. In this paper, the advertiser is considered to be value maximizer. So the value maximizer is an advertiser that is interested in maximizing the advertiser gets the value VI in the ith auction. So the auctions are numbered with letter I. This one is the click-through rate of getting slot J in the auction I. This means that the auction is actually multi-slot auction. So this XIJs, those are the allocation of the advertiser to a slot in the auction I to the Jth slot, and it is assumed to be a binary variable. So if it's 0, then the advertiser is not allocated to the slot J in the auction I, and if it's 1, then it means that the advertiser is actually allocated to that slot. So when the allocation happens, when the submitted bid is good enough to win this, the advertiser gets a chance of a click, which is characterized by a click-through rate. If the click happens, then there is a expected value of a click, and the expected value of the click is basically composed of the conversion rate and this expected order value. Important here is that the goal of the value maximizer is to maximize the value, and this is actually in contrast to a profit maximizer. So the alternative would be a profit maximizer, and the profit maximizer would maximize profit, which is value minus the sum of all payments. For the case of value maximizer, we need to provide some additional constraints. And the first constraint is the budget constraint. And this is saying that the sum of payments, and the payments are per click, so these are costs per click, times the probability of the click, which is the CTR, and times the allocation, so whether the advertiser was allocated to the slot or not. This total sum of all payments should be less or equal than the given budget. In the modern ad systems, the assumption is that the advertiser does not only provide the budget, but also provides a performance constraint. And the most popular performance constraint is the constraint on return on spend. This constraint basically says that it's not only important to not overspend the budget, but it's also important to make sure that we are getting the value at a rate which is acceptable. So this is the minimum acceptable return on spend. So for every dollar that we spend, that the advertiser spends, we want to get at least R times value by selling the product. The approach taken in the paper is to apply the so-called linear programming LP relaxation, converting the integer programming problem here, where the decision variable xij belongs to a set of either 0 or 1. This is relaxed, and now the xij is in the interval of 0 to 1. So this is basically saying that for the sake of making the problem much simpler, making it a convex optimization problem, making it a linear program, we relax this condition and allow fractional allocations. So this is saying we allow fractional allocations, and therefore we get another constraint on this allocation variable xij's, saying that all of them should be positive. Another assumption in the paper is basically this is a unit demand assumption. At most, one slot is allocated to this advertiser. So the sum of all allocations to all slots should not exceed 1. So this is the unit demand. So now we are ready to get to the technical part of the paper and actually write out the main optimization problem. And the strategy is, because this is a linear program, we are going to apply a standard approach. We are going to consider the dual problem, and then we are going to consider the optimality conditions, which are the KKT conditions. And from these KKT conditions, we are going to figure out what are the conditions, what is this bidding strategy, and why is it optimal. The optimization problem should be written in the standard form, which is a minimization problem. So we are going to minimize the value, like the negative of the value. Now we have the constraint on the budget. Then we have the ROAS constraint. And we have two constraints on this allocation variables. This is the unit demand constraint, and this is for all I, for all auctions. And finally, we have that all xij's are greater equals than 0. So this is for all i's and j's. So let's pause here and let's think a little bit about this, because it might not be exactly obvious, like even why do we have this optimization problem. First of all, we are talking about this optimization problem with respect to the allocation variables xij. But on the other hand, in the system, we have the auction, and like, what is the connection? It's not us who is deciding on this xij's. Well, the assumption here is that the bidding agent is able to choose the bids in a way to choose the xij's, to choose the allocation, because all other competitors are fixed, and we assume that we kind of know what they want to do. And this is why the bidder is able to choose the bids in a way to actually execute on any allocation that we want to get. This is why this optimization problem is formulated with respect to xij's. The second big question is, how do we know the prices here? Because the prices here are actually defined by the auction. So again, the assumption here is that given that we know the actions of all other agents, and given that we know the format of the auction, we kind of know the prices that we are going to get in response to our bid. So maybe the bidding agent is able to simulate the auction, and this is why here we kind of assume that the prices are available. Well, in the real life, it's not going to be like this. But what is amazing about the result in this paper is that we are going to find that we don't really need to know. This is because this is the property of the truthful auction. Now the strategy here, the solution here is to, well, introduce Lagrange multipliers. Lagrange multipliers corresponding to the inequality constraints are going to be constrained themselves. They are going to be required to be non-negative. So for the budget constraint, we are introducing the Lagrange multiplier. We're going to call it mu, and this is going to be greater or equal than 0. Then for the ROAS constraint, we are going to introduce Lagrange multiplier tau, which is also greater or equal than 0. For unit demand constraint, there are as many multipliers as there are auctions, so these are the Ri's, and all of them are greater than 0. And then finally, for every allocation variable, we are going to have the Lagrange multiplier that is responsible for this constraint, for the constraint of this positivity. And this one is also going to be positive. Now the KKT conditions are basically saying that the optimal values of mu and the optimal values of xij's are connected by a complementary slackness. And this is saying that either mu is 0 or the constraint is tight. And the same goes for the ROAS constraints. And here we have the same complementary slackness for Ri's. So it's either Ri is 0 or at least one of the slots is given, and at most one of the slots is given. And then finally, there is a complementary slackness constraint here. So this is for all auctions, and this one is for all auctions and slots. So the next step is to consider the dual problem, and the dual problem is derived from the Lagrangian by taking an unconstrained minimum with respect to the primal variables. It's only meaningful if the stuff in the bracket is 0, then we actually get a meaningful dual. And the dual problem is going to be to maximize this thing. So what is important is that from this we get one more constraint, which is a part of this KKT conditions. Here we are going to use the complementary slackness condition. So now we can see that if we actually have an allocation, so if in auction I we actually allocated this advertiser to the slot J, then the corresponding lambda ij is going to be equal to 0. Assume that in this auction I, the advertiser is allocated to slot J. So the slot J is actually where we got allocated. Then we have that Ri is equal, so remember lambda ij is now 0, so we can move the other terms to the other side. For some other slot k, so this is the J is the slot that we got allocated to, and the K is the slot we didn't get allocated to. So for all other slots K, we have that Ri is going to be larger or equals. So it's easy to see, because if we didn't get allocated, so X ik is equal to 0, then lambda ik is greater or equals than 0. And now this is what we wanted to get. So we have the optimality condition here. So just by rearranging the stuff a little bit, we can make it look just slightly different by dividing by this. And from this we see, this is the observation that is made in the paper, that this term here is actually precisely what we want to bid. So the proposal here is to use this term as the bid. This is great because this is very simple, and this is why the strategy is called uniform strategy, because it says that in all auctions we should bid proportional to the value, and the multiplier is the same for all auctions. So it's kind of possible to choose the optimal and single optimal multiplier that would be multiplied by the value. And this is why the strategy is called uniform bidding, because it just prescribes to find a single multiplier. So for this to work, we have this condition that bi minus pij, so for getting allocated in slot J by selecting the bid bi should be greater or equal than getting allocated to any other slot K. And this is a very, very important condition. This condition is saying that it's the task of the auction to make sure that when the bidder submits bid bi, the slot that is chosen by the auction, that should be the slot that is the best slot in the sense of the profit maximizing in this particular auction. The underlying auction should choose to allocate the bidder in the slot that maximizes this thing. And this thing is the profit, but this profit here is in one auction. So remember, we have the advertiser, who is the value maximizer, and the result that we just got here is that the optimal strategy is the uniform bidding strategy with this particular multiplier, if and only if the underlying auction is able to implement this condition. So it is able to allocate the bidder to the slot that is the optimal slot for this auction, for this bidder, in the sense of profit maximization. The underlying auction still needs to be truthful for profit maximizing agent. Now let's spend a little bit of time making sense out of this uniform bidding strategy. So to do that, we need to bring back the complementary slackness conditions for budget and ROAS. And by complementary slackness, it's either mu is 0 or we are actually constrained by the budget. So the term in the bracket is equal to 0. So from here we see that when we have basically infinite budget or very large budget, the mu is equal to 0 and the tau would be chosen in such a way that we would meet the ROAS constraint. And it's interesting here to take a look at the limit of tau going to infinity. So when the tau goes to infinity, we end up with bi equal to vi over r. And this makes a lot of sense, because if the force of this constraint is very large, we want just to make absolutely sure we are not overbidding in order to get the ROAS constraint. So we are not going to bid any higher than this. But in the situations where there is some space, we actually are going to bid a little bit more aggressive, a little bit higher. The last thing I want to do in this video is to touch a little bit on the application of the uniform strategy in the first price auction. When all the advertisers are forced to use the uniform bidding strategy, there is a good equilibrium in the market. So here I want to use this duality argument to show what happens if the user if the advertiser uses the uniform strategy in the first price auction. The RI, this dual variable for the unit demand, is equal to Cij, which is the click-through rate. So this is divided by mu plus tau r. Cij, here we have 1 plus tau over mu plus tau r vi minus the payment ij. And this is for if we get allocated to slot j. And ri is over this tau r is greater or equal than Cij 1 plus tau mu plus tau r vi minus pik. So this holds for all the slots where, so we can only get allocated to the slots where the bid is larger than this price. And well, when it happens, we can put our bid here, and the bid is constrained to be a uniform bid, so it's going to be some gamma times vi. The argument here is that for the slots where the minimum winning price is lower than our bid, we are not going to get allocated. So we will have the lambda ij taking care of this slackness, of this KKT condition here. But when our bid is enough to win, so we can maybe outbid the bidders below us, then the payment is going to be equal to our bid, and this is going to be this. And now we can plug it in both equations, and from here we will see that Cij times vi times this 1 plus tau mu tau r minus gamma is going to be greater or equal CIK VI times the same thing, TI tau mu plus tau r minus gamma. So this stuff cancels, and we end up getting that the condition for this to hold is like this. And this applies only to the slots that we could win with our strategy, with our uniform strategy. And this is saying that the underlying auction needs to be monotone. And remember from the video on the necessary and sufficient conditions for rationalizability, which is basically that making the mechanism truthful. In the single dimensional context, we also had that it is a necessary and sufficient condition for the auction to be truthful is that it is monotone.